So this is lesson 4 of year 13 thermodynamics. This is looking at enthalpies of solution. So we're going to have a couple more definitions, which are enthalpy of solution, enthalpy of hydration. We're going to focus in on using Hess's law to calculate an enthalpy of solution, and you're also going to end up using lattice enthalpies. So this is just building on year 12 work. So here are those definitions. Again, you must learn these and make sure you are pitch perfect on them. So the standard enthalpy of solution, which is the first one up here, delta H sol, is the enthalpy change when 1 mole of ionic substance is dissolved in water to produce aqueous ions. Okay, so let's give you a definition of that by providing an equation. So here is 1 mole of your ionic substance, sodium chloride solid. Again, make sure the state symbols are really important here. Make sure you always include them. So to produce Na plus Aq plus Cl minus Aq. Okay, so that is a standard definition, and that's the kind of equation that you need to be able to write for this. Standard enthalpy of hydration, delta H hydration, is the enthalpy change when 1 mole of gaseous ions are hydrated in water to produce aqueous ions. So to explain that to you, make a little bit more sense, it's when you're taking 1 mole of gaseous ions to produce 1 mole of aqueous ions. This may seem not make sense at the moment, but once we show the Hess's triangle, this will start to make sense to you. So you need to have a good understanding of what's actually happening when you are dissolving an ionic substance in water, which is our polar solvent. So if you imagine you've got your ionic lattice here, which you should be familiar with, we're just showing one layer of it, so instead of the 3D version where you've got many layers, but obviously you won't have just an isolated set of ions like this. What's happening is that the water molecules, which are these little red and white blobs here, are coming in and they are surrounding each of the ions. So note very carefully, look at this chloride ion. It is surrounded by the water molecules, but the water molecules have got their hydrogens facing inwards, of course, because remember you've got your dipole, HOH, this is your year 12 stuff, delta plus, delta minus, delta plus. So these little delta pluses are what's going to be surrounding the negative charge of the chloride ion. And obviously conversely, you've got the sodium ion, and that is being surrounded by the water as well, but in this case it's the oxygen with its delta minus charge which is attracted to the sodium. Okay, so this comes in, and so basically the water molecules are breaking it up and surrounding each of the ions individually. Now you must make sure that you understand, you know how to draw this, and that you can perhaps draw an example in the exam. So let's say if I was drawing this, I would be drawing like that. So Cl minus, delta plus, and then drawing some little, get the right colour, change colour there. So it's a dotted line there, dotted line between there to show that there's an interaction. So this is the equation for enthalpy of solution. We've actually already learnt that. So if looking back at our definitions earlier on, this could write above this arrow here, delta H sol. Okay. Right, so we are going to be calculating the delta H solution when we have been given delta H hydration and delta H lat, which we calculated from Born-Haber cycles. Obviously, I'm just going to show you this way how to calculate delta H solution. When you come to an exam question, you may have delta hydration and delta H solution. You're being asked to do delta H lat. It's just a matter of writing an equation and solving for x. So, what we're going to do with these is we're going to draw a Hess's law triangle, and quite simply you can always do the same thing for these. So always write the gaseous ions underneath. Okay. So this we've already seen. This is our delta H lat. Okay. This is our lattice enthalpy. It's the energy that is released when 1 mole of ionic substance is formed from its constituents gaseous ions. Okay, so we're happy with that. Now, this one here is another new definition that we've just learnt. We did an example for earlier on. This is delta H hydration. Oops, sorry, bad writing there. hydration for Na and Na plus, and delta H hydration for Cl minus, so delta H hydration. So what you're going to be able to see is we're going to do a Hess's law. So when I say Hess's law, we always start at the non-arrowhead end of the arrow, and instead of going along the arrow, we're going to go back this way and along that way. Okay, so start the non-arrowhead, we're going backwards along here, so delta H solution is going to equal minus delta H lat, and then remember that we are going with both of these arrows, so it's plus delta H hydration for Na plus and plus delta H hydration for Cl minus. Okay, so I will show you that with the numbers on the next slide up. So here we go. They've drawn their triangle the opposite way up. So what they've said is that here's your lattice enthalpy. Okay, so they've actually shown, right, lattice dissociation enthalpy, that's LD, okay, rather than lattice enthalpy of formation. Obviously they're equal and opposite. So that's what they've given there. They put that on that arrow, and then this is delta H hydration. So in their case, they're following with this arrow, so it's going to be plus 787. Okay, and then it's going to be minus 405 and minus 364. So delta H hydrations. So that's going to be your delta H solution for this. And I'll just double check what the answer is for that and pause for a moment. So that is plus 18 kilojoules per mole. Usually these numbers are relatively small, okay, so you're looking like sort of, you know, 10s and 20s plus and minus. I'm not saying you won't ever find one that's a little bit bigger, but so sense check, make sure they're kind of relatively small. Right, the only way that these delta H solution questions get a little bit harder is where perhaps they give you delta H solution and you're actually asked to work out delta H hydration or the lattice enthalpy, or perhaps there's this example here where I'm just going to highlight you need to watch out when you've got two chlorides here. So sticking with our recipe for this so far, so this is magnesium 2 plus KCS plus 2Cl minus, KCS going to MgCl2, so this is our delta H lattice enthalpy. Okay, this is our delta H hydration of Mg2 plus, and this, take care, is twice the delta H hydration of Cl minus. Okay, so let's say you have been asked to work out the delta H hydration for Mg2 plus. Okay, so what you can do is you can write yourself an equation and then solve for that. So you can say that delta H solution is going to equal minus delta H lat, because of course we're going backwards along this arrow, plus delta H hydration Mg2 plus 2 delta H hydration, I hope you can't hear the kids in the background, Cl minus. So let's say this here is the missing quantity, just stick that in there, stick all the numbers in here and solve for that number. So something that you might also be asked about in an exam question is the trends in delta H hydration within a group. So you'll notice here that as the iron gets smaller, delta H hydration is higher. Okay, so you should be able to use your knowledge from year 12 so far to think about why that might be so. So think about this iron here, lithium ion is small and highly charged relative to a potassium ion, where that single positive charge is spread over a much larger area. So what you want to think about is the fact that this lithium ion has got very high charge density, which means that any water molecule is going to be very highly attracted to it. Same goes for fluoride. And again, you can see that down the group, delta H hydration decreases as there is less attraction between the iron and the water molecules. So the other part of the equation, a little bit like when you did the perfect ionic model, we talked about The size of the ion, but also the charge of the ion is very important. So in this case, as you can see, the higher the charge on the ion, the greater the enthalpy of hydration, because the greater the attraction for the water molecules. So some of the sharp-eyed amongst you, those of you who remember your Group 2 chemistry from year 12, might start to sort of think there's something weird going on here, because remember we learnt about the Group 2 sulfates, the solubility decreases down the group, because remember barium sulfate is your barium meal that's toxic. Barium compounds are toxic, you can quite happily eat it because it will come straight out the other end. But the solubility is opposite for the Group 2 hydroxides. Well, hang on a moment, so this ion is getting bigger, so delta H hydration from here to here should be getting smaller. So, but how come we can have a different trend, that this is becoming insoluble, and whereas this is becoming more, the hydroxides are becoming more soluble? So the issue here is not actually to do with enthalpy. Okay, so what you're going to learn about in the next 2 lessons is going to be about something called entropy, which is actually the real answer as to why different compounds are soluble or not soluble. I will just flash up quickly some data, and I might put that in another set of slides as well, which if you want to sit down and work some of these through, feel free.